Hello everyone, and this is physics. In this video, we want to continue discussing resolving vectors into the xy components. And this will be part B. In part A, we ended here, where we found what the equations were. We derived the equations for the x component and for the y component with respect to the angle theta and the magnitude m of the vector. So we're going to go ahead and continue this now using vectors and solving a problem using vectors using these two equations. So let's carry on here with part B. So consider a vector. A vector is generally depicted as an arrow, and normally we begin with the arrow going to the right and upwards. So we'll do a vector something like this. Start here, straight line going in that direction. And there's two parts to a vector. Vectors, they got magnitude and a direction. And vectors are generally shown as an arrow. We call this right here the tail, and here is the tip of the arrow, the tail of the arrow. Sometimes this is called arrowhead, or sometimes I shorten it to just simply the head, and this is the tail. And it needs to have a magnitude. And for our purposes, we're going to use a force. A force is a push or a pull. For instance, if I pull this book right here and I'm pulling it out towards me, I'm using a force to pull it. I can show that force by using vectors coming towards me. In this particular case, I've got this force going in this direction. So imagine here is something I have here, and I am pulling on this in this direction. The object is moving forward as I pull on it in this direction. That's what that vector represents, but it needs a magnitude. So if I had some means of measuring the force, and let's say I've done that using some instrument, and the force in that direction is 15 newtons. And newton is a unit of force in the metric system. Now this also needs a coordinate system in order for us to give it a direction. I just can't say 15 newtons in that away. So I'm going to use a different colored pen here. For a coordinate system, in order to give this an angle, some direction, I'm going to use the standard XY plane. So going in that direction, that's the positive x-axis. Going in this direction, the minus x-axis going up. Positive y-axis going down is the minus y-axis. So this is the standard Cartesian plane. And the vector is going in that direction. So if I were to give it an angle, if I were to take a protractor and measure this angle right here, it sweeps upward from the positive x-axis upwards. And let's say I make that measurement, and I call that measurement, looking at it, it almost looks 45. I really don't want to use 45, so I'm going to come up with 25, 30, some odd number. There you go, 32 degrees from the x-axis. So it's 32 degrees from the x-axis, pulling with a force of 15 newtons. This is the definition of a vector. It has magnitude and direction. And what we want to do today in this video is resolve this into its x and y components. This is done because sometimes forces in an angular force is difficult to work with. It's much easier to resolve it into its x and y components and work with forces completely horizontal, completely vertical, rather than dealing with them at this specific angle. Now this doesn't have to be newtons. It could also be in 15 meters per second, 15 meters per second squared for acceleration. For our purposes, I'm going to use a force. And forces in the metric system, forces have the unit of a Newton, represented by their capital letter N. Having said that, I'm going to redraw this down here just to clean it up a little bit. one property of vectors is they can be moved around as long as they're on the same plane, and this is the plane that I'm working with here, have the same magnitude and the same direction. I can take that vector and move it anywhere. That is a property of vectors. So I'm going to take this vector, I'm going to move it down here. Give me some room so I can go ahead and resolve it into its two x and y components. So that vector that we saw earlier, I'm going to put it here. And it was going something like this, not to scale. And we had a coordinate system. We had an xy coordinate system that goes with it. So this is the positive x-axis going that way. And the positive y-axis going up, and minus y going down, minus x going to the left. I placed the tail of the vector at the origin, 0.00. Sweeping upwards, we said that was 32 degrees, and the magnitude of that vector, we said, was 15 newtons. So here it is redrawn. It has the two necessary parts for a vector, magnitude and direction. And we want to resolve this into its x and y components. To do that, we're going to project this vector here onto its x component, and we're going to project the vector onto its y component. And we do that by drawing a line straight down parallel to the y-axis. And this is done for visual purposes. Down the y-axis, and the x component, we draw a vector and the arrow. We already have a direction, 0 degrees. It's going along the x-axis. The magnitude of that angle, or that component, is m cosine theta. If you go back prior, wherever the angle is, the component vector adjacent to the angle, we're going to use the equation m cos theta. Now for the y vector, the y component, I should say, going up here, if I use blue there, yeah, I'm going to draw horizontal line parallel to the x-axis, as parallel as I can get it. Touches the y-axis here, therefore the y component would look like this, visually speaking. Direction is straight up, and it needs a magnitude. And to determine the magnitude or the length or the size of this y component, because it's opposite the angle given, it'll become m sine theta. We go back a moment. This is the general equations on resolving vectors. Here's the angle. There's the magnitude. If the component that we're looking for is adjacent to the angle given, we're going to use m cosine theta. For the component which is opposite the angle which is given, or the angle that is known, we're going to use m sine theta. So you could go back to first principles and solve that again, but it's easier if you just simply memorize m cos theta, m sine theta. What's important is to determine when do you use cosine, when you use sine, is with relationship to the angle that is given. If we're talking, if the component that we're looking for is adjacent to the known angle, we use cosine theta. Opposite to the known angle, here it is here, we use sine theta. Let's put in some numbers now. M represents the magnitude of the vector given. In our case, it's 15 newtons. Cosine times the cosine of the angle that is given, 32 degrees. I'm going to put this in my calculator now. Be sure your calculator is set to degrees. I have this here set to degrees. And you notice on my calculator I have all the digits shown. going to put in cosine of 32. Cosine 32 degrees is equal to, and it gives me a number. Cosine of 32 degrees is 0.848804896. Originally, this has a unit. It's called degrees. But once you do take the degree of a number, 32 degrees, the number that the calculator gives you is a dimensionless number. It has no more units. The degree units drops out. And we'll take this number now, and we're going to multiply it by the 15 newtons. If not multiplied by 15, it's 15 newtons. Wherever we move the 15, the newtons, the units have to go with it. They're a married couple. So 15 newtons. And once I do make this in a calculator, take the 32 degrees, it becomes a dimensionless number. Multiplying these two together now, I already have the 32 degrees already in my calculator. It's multiplied by 15. That's equal to, so the x component, I should say, the x component, the positive x component, because it's going in the positive x direction, is equal to 12.7207214, and the only unit that's left over is the Newton. Lastly, we need to reduce this to significant figures, proper significant figures. We look at the original question. The measurement, even though I showed you how to make the measurement, what I was attempting to, as far as measurements go, I chose 15 newtons to two significant figures. And the angle in my imaginary protractor, I called this to be 32 degrees. So I made this measurement to 2 sig figs, that measurement to 2 sig figs. Therefore, the final answer needs to be reduced to 2 sig figs. The x component is approximately, look at that third number, round up or down, based on if it's 5 or greater, round up. So this will be 13, and the unit is newtons. Now we can do the same thing now here for m sine theta. I'll try to work around this. Okay, this is approximately 13, and it's plus 13 newtons because we're going in the positive x direction. Let's do the same thing here now for the y component. And I started with blue, and I'm going to carry on with blue. Putting in the numbers now, m represents the magnitude of the vector, which is 15 newtons, times the sine of the opposite angle, not the sine of this angle here, but the sine of the opposite, which is 32 degrees, which was given, 32 degrees. Similarly, I'm going to scroll down here a little bit. Sine of 32. Sine 32 is equal to, now this number is now a dimensionless number. The degrees drops out. Going down here, sine of 32 is 0.529919, and I'm going to stop there. I'm running out of space. Multiplied by the 15 newtons. So the y component is equal to, multiply that number times 15. I already have all the digits in my calculator, so I just simply multiply by 15. Is equal to 7.948788. And the unit is the Newton, because here that becomes a dimensionless number. The y component, or approximately, reduced to proper significant figures. 2 sig figs were given. Therefore, we're going to reduce this to 2 sig figs, 7.9. Look at the next one. And 1, 2. The next one's a 4. And we're going to round down to 7.9 newtons. And it's in the positive y direction. Positive y direction. We have effectively then split that 15 newtons into its x and y components. If by some chance you happen to get a number here for any of these components, which is 15, the original number, or greater, you made a mistake, because these components have to be less than the original vector. The magnitude of these components are always less than the magnitude of the original vector. Obviously here it's less than 15, so that we know this is correct. And this component is also less than 15. None of this is to scale, obviously. So let's do this again. I'm going to resolve one more thing before I go further. Once we have resolved the vectors into its x and y components, I'm going to draw that Cartesian scale again. Plus x direction going that way, plus y going upwards. Here are our two vectors, our component vectors, 13 newtons to my right. 13 newtons to my right, and we said the other one was 7.9 newtons up. 7 points about 8. Try to keep it to scale. So that'd be the y component and the x component. Once we've done this, the original vector is no longer there. That's because we've taken it and split it into its two components. So it no longer exists. It's gone. This is what we have left. The two components. You can, and I won't do it in this video, use simple trigonometry and go back to the original vector, which is just the hypotenuse of a right angle triangle. But I'll leave that for you to do. So let's do another example of resolving vectors into their x and y components. Let's take another vector now. This time I'm going to go to my left. And I'm going to exaggerate it. I'm going to start here. Here's the tail of the vector and the tip of the vector. It needs a coordinate system. I'm going to put the tail here at the origin of an xy coordinate system. Going that way is plus x. Going that way is plus y direction. Going down, minus x direction. And going this way is minus y direction. It needs a magnitude. So if I take something here and I'm pulling on it at some angle and it's moving forward, I'm pulling. And I have some kind of instrumentation here in order to make the measurement. Let's give this thing here a magnitude or size. Again, we're going to use force measurements. Looking at that, we'll go with different kinds of numbers. 11 newtons. And for the angle, I could choose this angle here. But instead, I'm going to choose this angle. With respect to the y-axis, I'm going to make a measurement, get a protractor, and measure this angle. Here's 45, 50, 60. We'll call this that angle in here 67 degrees. So here's my vector, 11 newtons, 67 degrees, swinging to the left of the y-axis. So we're going in the negative, oh, my mistake, this is negative x, minus x-axis. Plus y, oh boy, minus y. I got this plus y minus, yep, okay, we're good to go now. So let's resolve this here in its two components now. Same as before. Drop the tip all the way down till it intersects the x-axis. Parallel to the y, so this will be the x component. And doing the same thing for the y. This is now the y component, and the angle is 67 degrees. The equations now that we're going to use for the two components. This component here in the y direction is adjacent to the angle given. We're going to use m cosine theta, because cosine is used when the angle is adjacent to the component known that you're seeking. And this one will be m sine theta. Let's have a look at this now. M is the magnitude of the force. So this is the y component is equal to y in the positive x-axis, so it's going to be a positive. And the value here is 11 newtons. M is 11 newtons. Cosine, the angle given is 67 degrees. In the prior example, we used the y as the sine of is that the sine of I'll get it here, 32 degrees. Get that in the y component. Again, it has nothing to do with whether it's in the y direction or the x direction. Whether you use sine or cos depends on the angle that is given. So let's go back and finish this. We have the equations. We have some numbers. So in the y component now going up, this will be the magnitude. Y component. I'm going to put that in my calculator. And this time I'll just simply go 11 times the cosine of 67 degrees is equal to 4.298042. And the unit, again, is the Newton. And this gets reduced to 2 sig figs, 2 sig figs. Y component then is approximately 4 point, and look at that third one, it's greater than 5, 4.3 newtons in the positive y direction. So this will be plus 4.3 newtons. According to my coordinate system, it's going in the positive y direction. Now let's do the x direction. M cos theta, it's 11 newtons. Sine 67 degrees. This would be the x component. It's actually the minus x component, but it's x component nonetheless. Putting this here in my calculator, then the x component is equal to, putting in the numbers, 11 times the sine of 67 degrees is equal to 10.12555. And the unit's going to be newtons. But this time, the direction here is in the negative x direction, so this has to have a negative sign. It's minus 10.1 according to a coordinate system which we have built here. Along the x component has to be minus 10 going in the negative direction. So the x component, approximately, if we're going to go to 2 sig figs again, reduce this down to 2 sig figs, that's minus 10 newtons. This is important. When we do the algebra in adding vectors together, once we resolve them, that negative sign and this positive sign become important for the algebra. And how do you get this? By drawing your coordinate system and seeing which way negative is and which way positive is. So these are two ways in order to resolve vectors into their x and y components. The equations that are used, the general equation that is used, it's generally shown like this. Here's a vector. Here's an angle theta. The x component, I should say, is, and we'll give that a value m. Since this is adjacent to, but not always, as I showed you earlier, it's adjacent to the angle m cos theta. The magnitude of the vector is m cos theta, and the component. And the magnitude of this component, the y component, is m sine theta because it is opposite that angle. That's the general depiction of resolving vectors in their x and y components. And then there's always the little things that happen when vectors go in the opposite direction and you wind up with these kind of situations. And with that, and this is physics.